Okay, so I hope everyone can see my screen. Thanks for coming to the webinar this morning. Well, morning European time, kind of evening Australian time. The topic of this webinar is about the outcome of the DDRI working group, and what I'm going to do is during this webinar I'm going to give you a bit of background for some of us who do not have the or haven't seen the initial or early presentations from me during the RDA plenary. Then I will talk about the adopters of the outcome of the working group and the new developments that are happening. I'm hoping to be able to leave at least 10 to 15 minutes at the end for questions and discussions about the project. So the concept of this working group initially started by addressing the problem of cross-platform discovery. The issue that we had, this is one of the earliest slides that I had from 2014 when we created the initial work that led to the working group. In ANZ in Australia, we are actually operating a discovery portal that's called Research Data Australia. And one of the functions of this portal was identifying the related data sets using the DataSite DOIs. Well, we were using the REST API cross-platform search, and in this case we had a page. It is a collection that was curated, and you can find this in the Research Data Australia page. And in those days, we actually had a function that was going to DataSite API and was searching for all the other data sets related to this topic. As you can see, there are about 1,000 records as external records that we have identified from DataSite. The problem is that the keyword search cross-platform discovery is not really optimized to provide a useful outcome for the researcher if they want to find other things related to their work. When we were doing an earlier project that was related to the ORCID and DataSite, at that time there was a European funded project called Odin. And in one of the hackathons, Todd Vision from Dryad and myself, we were actually working on the concept of checking the records between ORCID and DataSite. And we found there are some better ways for doing this. So looking for some better ways of finding related data sets really led to actually creating the working group. And in the initial partners in the working group was Dryad, and CERN, and DataSite. And then we got a lot more participants from the RDA and institutions who were interested in this problem to basically they came on board and started contributed to the project. Now, when we were doing the earlier stage of the project, we tried different models. We tried different techniques using the ontologies, using different hierarchy of keyword structures, different data mining techniques. What we found was one of the easy way to actually connect information is using the concept of co-authorship and also joint funded grants. So that's what actually came as an outcome of the DDRI working group recommendation. We ran the initial case studies and some experiments that showed that we can actually connect data sets using the chain of collaboration based on the publications related to the data sets, and also about the funding information related to either the research that is connected to the data set or the funding that is directly connected to the data set. So during this talk, I will show you some of the examples and how these kind of connections can actually be established between repositories. Now, this is the next 4 or 5 slides are the examples that I have used in the last 2 years every time that we are talking about this problem. This is from the early experiments that we did, and it shows exactly how the process can be done manually by a librarian, for example, or a data manager. But then later on, we actually automated this process. So if you want to do this manually, you look at the data set in a repository. In this case, this is a data set from the University of Sydney in Research Data Australia. You can see the name of the author or the creator of a data set. You can actually search that person in Google. You find the profile of the researcher. You go to the list of publications of that researcher. You read all of them, and in one of them, in this case in the +1 article, we actually identify a dataset in derived repository that we can go there and we can see this dataset is by the same author. So what happened here? We moved from a dataset to a researcher to a publication, and publication to another dataset. Now, in the early days, we have done many of these experiments manually or writing some simple Python scripts that go through the publications. And that was basically the proof of concept that this model can work. But obviously, doing this manually is not scalable. So that was basically the idea of creating a more automated approach. And in that stage, we basically came up with the idea of the switchboard. That was a name that basically we kind of stole from the telecom companies, when in the past there were people who were connecting other phone lines, and then later on they were replaced by a chipset that called switchboard. So we tried to do the same thing. We created a software open source code that basically what it does those operations using the code that are running in the Amazon cloud. The system evolved a lot in the last 3 years, but this is kind of like an abstract layer of how this system works. We have a data provider layer that we are collecting information from different sources. A lot of them are actually happening using the OIPMH, and some of this information also collected using the specialized exported files from some of the providers. For example, in the case of NII, that is a National Institute of Informatics in Japan, the data is so large that we cannot actually harvest using the OIPMH. So we actually get the data using the Amazon S3 buckets. So we do the data transfer right on the Amazon layer. Then we have the source code, which is the switchboard. And what the switchboard does, it's resolve all the identifiers using the API and RESTful services on the web from the identifier providers like Crossref, DataSite, ORCID. We use the Google Search API, the enterprise system, that basically what it does, it enables us to search a particular paper in certain domains. The result is a JSON outcome that can be actually exported from Google in Dublin Core, and that is one of the inputs into our graph. And then we use the node linking process, which is a very simplified graph clustering method that helps us to resolve some of the duplicated records. We also do the metadata harmonization. The best way to explain this is, for example, the DOI in some metadata repository just called DOI, in some other one called identifiers and other identifier types. So there are different ways of expressing the same values in different meta models. We actually we kind of aggregate and simplify them into a graph model that we call this research graph. In addition, the other thing that we do is we actually, the whole infrastructure happens on the Amazon layer, and it has a RESTful API, but that is not particularly useful for exploring the graph. So one of the things that we do the export into the Neo4j graph database. So that's what a lot of data managers, they can use to explore their data. The graph model that we are using is basically is something that we adopted initially from the RefCS model in Australia. In Research Data Australia, we have a model that's called RefCS. And then when we move through this lightweight graph modeling, we also lean toward the DataSite meta model and ORCID meta model, so we can actually cover all the fields that we need. It is designed to actually hold the connections, not replacing the initial metadata values. So you can think about the fields available in this graph as a very, very abstract layer. So it tells you what is the publication, who is the researcher, how they are connected. But then if you want to know more about the researcher or the publication, you actually have to go back to the source. For example, get the metadata records from Crossref, or in case of DataSite, get the full metadata records from the DataSite records. And that's basically that those metadata repositories are the source of truth. The graph structure is just holding the connections that connecting those sources together. Now, What I'm going to do is to demonstrate what I mean by connecting the data sets using the collaborations and joint funded grants. I'm going to actually switch to the Neo4j environment that has one export from this graph, and I'll walk you through some of those examples so you can see actually how these connections can be established. So what I'm going to do is I'm going through the one hosted version of Neo4j. Basically what we are running here is a latest version of Neo4j with some extensions for the research graph meta model that makes the process of running the queries easier. One of the simplest things that we have added a tab on the left side so you can actually run the queries like search by DOIs, by DOI prefix, find records by ORCID, or find the shortest path between two different DOI. So in this case, let's actually find a data set by the DOI of the publication, from the data set in the Dryad. So in my example, I had the DOI from the Dryad. What I'm going to do is I'm going to actually just replace this with this. So you don't actually need to know the query. You can just replace the value that you need. And what the query does, it finds you that given data set. Now, a data set here is actually have some metadata, and you can find these records here. So it gives you the DOI record, the title, and the authors, and that's about it. So there's no further metadata available for this record. But when we expand it, we can actually get all the other connections related to that. So we can see all the other data sets, all of them are in Dryad. We can see the +1 article, and we can see the researcher. Now, this given researcher is actually came from our integration with Google API. Now, I can actually expand this to give you more space, and then I can actually expand this researcher. So when I expand the field, it actually goes to the graph, and it brings all the other information related to that researcher. In this case, all the blue dots are the list of publications, and the grants are kind of yellowish type color. Now I can expand all of these grants, and I can find the other information related to those. Now, the way that this system actually works is it enables you to do this crawling through the graph using the much simpler query. So in this case, what we have found is, if I'm not mistaken, one of them, maybe this record. Yes. So yeah, this record, this was the initial data set, if I'm not mistaken, from University of Sydney. That is the record that I had in the initial slide. So the title of this in the bottom of the page might be hard to see on your screen, is exactly the same data set that we had in our first slide. So we basically went from that slide to this slide. Now, one thing I can do in this environment is running the queries that find all the related data sets with much simpler query. What we can do is that we can say, I have a data set here, and give me all the other data sets here with the 3 degrees of separation. And then we return the dot title. Just to be sure, I previously tested these to be sure they're correct. Yeah. Well, I went for 4 degrees of separation here, and I can run this, and I get the title of all the other data sets in my database that's connected with the 4 degrees of separation. I can be even more specific here. Rather than just looking for a data set, I can looking for a data set from particular source. So I can say I want to see a record from ANS that actually connected to this data set with this criteria, and it has a DOI. Now, everything I'm typing here is available as an API, and that's one of the outcomes of this project, that this information through the API is accessible to our partners. So when I run this, I can get a list of all the other DOIs that are connected to this with 4 degrees of separation. And to illustrate what it means, actually, let's see, I have a question. I'll answer the questions after the technical demo. So what I can do, I can actually find how this DOI is actually linked to the initial DOI. So there is another query. Sorry, I actually, just to be sure, I cheated here and I saved this query before. But I'll explain how to actually get to this query. So if you want to type this query, actually there is an option here to say shortest path. And here you click on this and then you type your DOIs, 2 different DOIs here. And then what it does, it actually gives you this query. So in this case, I have 2 DOI and I want to know how they are connected. When I run this, it says, well, these 2 DOIs are connected in this way. The first dataset is linked to a researcher, researcher is linked to a publication, and publication is linked to another dataset. I was actually looking at the Dryad website. So this is this particular dataset from Catherine Bilov. And when I was exploring the Dryad, I found there is another dataset that I was looking at this and I found these 2 are connected. Now, if I am in this scenario, if I have 2 different DOI, and if I want to know how they are connected, I go back again to this query. This was my Catherine Bilov dataset, and I replace this with this DOI, and I get the new connection. So this shows these 2 are connected by a grant. So the author of the second dataset is actually Claire Wade, who's collaborating on a grant, and that grant or project is linked to Catherine Bilov and also linked to this dataset. So before I continue on this slide, let me see if I can answer this question. If I can find how to do it. For some reason, I cannot get that screen back on. Okay, I'll leave this one for the end. I'm assuming you still can see my screen. Panagiota, if you do not see my screen, please let me know, because for some reason I cannot bring the control panel for a chat box.
We can see your screen and we can hear you very well.
Okay, so I'll continue, and at the end we get back to the question. At the moment I have a bit of problem with actually bringing the chat box screen back to the front. Now, so this is some examples from the connections with the 3 degrees of separation. You have a data set that it is linked to a researcher, researcher is the author of a paper, and paper is cited in another data set. You have a data set that actually been cited in a paper, the paper also cited a grant, and the grant metadata shows another data set linked to that. We have examples of this in Research Data Australia. And we have data set that is actually, it has a creator, and the creator, the researcher, is a participant in the grant, and the grant actually has cited another data set, or a data set cited the grant. So these are some of the examples of connection between data sets using the multiple degrees of separations. And using the recommended approach, and well, the recommendation is actually interesting term. Using the method that the working group participants discovered, in a way, that's the best way to explain this, we can connect the data sets in this model. I just want to emphasize something, is that this does not shows causality. It doesn't mean that dataset 1 and dataset 2, one of them is a result of the other one. This can be very, very misleading. The only things that it shows is that these datasets are in the same context, or in the same subgraph. So the chance that they are connected to each other is much stronger than just randomly searching a keyword in a much larger repository. And if you want to be more precise, you can actually do this keyword search and other form of data mining on the smaller graphs when you use this technique to find all the other connected data sets in that subgraph. So let's talk about the adopters. There are a couple of different early adopters that we had in this project. One of them was the NCI, which is a National Computational Infrastructure in Australia. NCI was one of the early adopters of the Switchboard source code. the way that they are using this technology is, well, NCI actually is a large storage facility and high performance computing infrastructures in Australia, and they have data from all different layers of Earth and different branches of science. Now, as a result of this, there is a lot of collections in their storage facility, and what they have done is that they have used the switchboard concept to actually export all of those metadata records into a graph. And one of the other things that they have done is that they try to find isolated clusters, and then they use some other analytics top of their graph to identify the nodes that they're meant to be connected to other things. Like in this case, the institutions, they're meant to be connected, but they are not. And so that's where it shows some problems on the quality of the metadata. And that was a tool for NCI to go back and improve the quality of the records. The other example is the NII from Japan, which is National Institute of Informatics. The NII is a large data aggregator from all the scholarly works in Japan, and they have the multiple systems that holds information from different scholarly outputs. We are working with them as we speak right now. We did a pilot in 2015, and now we are working on a more production infrastructure. The scale of the data is very, very big, and it goes across many systems. And basically, what this technology enables them to do is connect those systems together using this graph meta model. And that's basically one of the slides from the early talks about the mapping of research graph to NII. This is where you see different graph nodes from different systems are interconnected. Now, the other adopter of this technology was, adopter and the main supporter of this project from early days was ANDS. And one of the things that we did in ANDS was we actually created an engine that enabled us to find the connections between the Australian collections and datasets and international collections. So we want to know, for example, what information in CERN Inspire Help repository can be linked to the information sitting in Australian repositories around the high energy physics, astronomy, and different fields in that domain. We created some more specialized code for that purpose. There is an instance of this code running under the research data switchboard.net, which is more like a prototype for our next generation of software systems with the integration of graph. For the interest of time, I will not actually show in those systems. I will skip through them. If there are questions at the end, I'll get back to them and I'll talk more about those. The University of Sydney was one of the early adopters. They used this technology internally for linking the research portfolio of different departments and basically identifying the impact of different research projects in the university and collaboration with different universities in Australia and overseas. We started just a project with GASIS in Germany to extend the concept of research graph to in a couple of different areas. One of them is the control vocabularies to basically map the graph elements to different vocabulary ontologies. Also, it's not just mapping the text to the graph, it's also about the graph modeling. One of the problems you have in this domain is the graphs can be very complicated if you just map all the possible fields together. And the problem of the complex graph is that it has overhead on the computation and also have a problem with the visualization. So if, for example, let's say there's a field that's called biology, and if you have majority of your articles are connected to the field biology, and then you try to find everything with the 2 degrees of separation, the moment that you hit the element biology as a node in the graph, then it will bring everything that's connected to the biology, which is not quite fruitful from perspective of finding the related information. So there are some challenges we have in this domain. We are also working with GASIS to connect our information to the organization graph. More specifically, we are exploring right now connections to the GRID database from Digital Science. The other projects that is at this stage, at the pilot stage, is RMIT University. They are also adopting the same technology for identifying the collaboration between different departments and different portfolio of research in the university level. So this is some of the examples I have from the adopters of the project, but in general, majority of the participants in the working group, each one have some interest in the technology that we have developed during the lifetime of the working group. And we get feedbacks from different partners from different experiments. Some of them actually branch off to be a different version of this activity. Now, the time that I have, I'll actually talk about a couple of new things that we're working as extension of this work. And then I believe we will have time for some questions and answers. Now, one of the things that we're working on this right now, well, it's been for about 12 or to 13 months, is a concept of a distributed graph. One problem that we have in creating the graphs like this is, first, not all the data are public, and I will explain what I mean by that. And secondly is not all the data can be set on the one computation center. It's once the graph gets bigger and bigger, the computation requires for holding the data and processing and traversing the graph can be quite expensive. So just give it some example. If you have the repository that has about 100,000 collections in it, if you download our main graph cluster, it's about 10 million nodes. Your repository with a scale of 100,000 datasets can be actually run on a normal machine with a quad-core CPU and 16 GB of RAM. But once you have the larger graph, you actually need a machine with 60 GB of RAM, and majority of infrastructure cannot actually hold that kind of required computation hardware. So the problems that we had was, one was reducing the cost and the technical requirements for implementing this technology for the partners who wanted to implement something like this in their own environment. And the second one was, we also have the cases like the universities that the universities are the main client for this, this business case. The case that they actually hold the information which consider relatively private. So universities, they have information that are curated about the research portfolio, and that is typically sitting in the research management systems. The information holding in that domain, as we speak right now, it's not quite clear that how it can be publicly available. Some of that information considered private, especially when it gets around the grant and funding and project descriptions. So one problem that we had was connecting our public domain graph to those private curated graphs, if you like. And that basically led us to creating a process that's called synthesizing module. Now there is a new component in the Switchboard that does the synthesization between two different graphs. The way that it works is that if you have a graph that you created from your own repository, what it does is that it goes to the larger graph and then look for every single node that you have in that larger graph and says, okay, can I find it? If it finds it, it brings everything that is connected to that node, plus all the other nodes that are connected to those nodes. So that's where we go to the multiple degrees of separation. You can actually synthesize a graph with 1, 2, or 3 degrees of separation. Depends on how much data you want to pull to your own environment. And the synthesize can be in both directions. Depends if there are two different public repositories they operate. They can be in bidirectional, or it can be in just one direction when it pulls the information from public to private. Now, this is just one example of how these things can actually operate. But for example, in ANDS, we run a version of this switchboard, and it can be operated on a Nectar infrastructure, which is a cloud computing infrastructure in Australia. Then we have the ORCID graph that it is currently hosted in the Amazon Web Services. And then as we are working with GASES, we are building the graphs that's hosted on the GASES infrastructure. So you can have a data set in JSON that's actually linked to a graph in AND's infrastructure, and then that information connects to a data set, and that data set connects to some publications and the researcher profiles in the ORCID graph. So you will have different graphs that are hosted in different infrastructures and are linked together. So the linkage between them are known to those graphs, and then when they want to do the sensitization, they bring those information to their own side as they are required. Now, the other activities that's happening right now is one of the kind of main development items in our pipeline right now is integration with the JSON LD and supporting schema.org. So this happens result of one pilot earlier that we were working on the concept of creating the RESTful service that can actually provide the graph structure to other systems without running the Cypher queries. Basically, you say, I have this UI to that. And we wanted to do this using the JSON rather than the XML. The primary reason for this is that JSON is much more computationally inexpensive. So it's not as expensive as XML. And also on the storage facility that we need to keep these records and the bandwidth that we need to provide this data, JSON is much, much more efficient. So we started using JSON LD, and one of the prominent schemas in the JSON LD is schema.org, which is basically a project backed by the Microsoft and Google, Yahoo, and other search engines. And we did a pilot on this to publish a paper in Big Scholar workshop in Perth in early this month, this work. And what we found was, well, we identified a couple of problems, and one of them turned up to be quite a valid problem that other people also acknowledge this issue. So now I'm here. Actually, I will go back to this slide, but I'll just get back to the schema.org. So when we did the mapping on the schema.org initially designed for making the information on the web more understandable to the search engines. So it has a concept of items and shopping bags and collections, videos, different things that you can find on the internet. But also it has concepts that can be mapped to what we need. It has an article, and it has a scholarly article that maps nicely to the publication. It has a concept of person can map to the researcher. That's perfectly fine. We have the research data. Well, we have the research data, and then in the schema.org we have a data set. What is missing is a concept of the grant. So a grant is something that at the moment, well, as the topic of grant, it doesn't exist in the schema.org. The closest that we found was either you can use something that's called action, or the other thing that's called offer. Now I'll explain each one of them. So action has those concept of something that happens in a time frame, and then the offer is something that is almost attached to the funding and money. It's almost like a bucket of money available, or something that we purchase a certain way. None of them obviously is a correct match for grants, so it's one of the missing elements in this context. And the other thing that we found was there is a lack of support, lack of direct support for DOI. So for example, for books, there is an ISBN field, but to identify DOI, you need to use a generic identifier field. And the side effect of that would be, if you do the computation on the graph, just searching for the records with DOI, that would not be as easy of having the DOI field directly as one of the elements of publication. Of course, when we are in this talking about identifiers, the other things that are missing and would be great to have is adding the ORCID to the person field or a researcher concept, and then support for other identifiers such as the persistent URL, the Perl, Scopus ID, and so forth. So if you are interested in JSON LD concept, there is if you like, there's a playground on the JSON LD website that you can actually type your own basically JSON object, and you can use different contexts to convert this to different formats. If you are interested in this, I highly encourage using the tool on the website. It's actually quite useful. Now, we actually have our mapping available on the web under the GitHub research graph / schema, and then you will be able to find the JSON LD folder that shows the context. And you can see that a lot of mapping here are quite direct. Things like, for example, URL is a URL, title is a headline, author list is just author. So it's a lot of them are reasonably straightforward. Now, this, I think I can actually finish the set of slides here. If you are interested to know further about the project, we have the 2 repositories on GitHub. We have the repository for the RDA Switchboard that holds the main inference engine. And then we actually have the research graph repository, which holds the majority of the tools that we are using, the crosswalks, a lot of works that we're doing in the publications are available in here as a public information. The schema available under the researchgraph.org website, and then you can find the list of collaborators on the same website. Given the time that we have, I think I should be able to switch to the other panel and open for questions and answer. Now, I have a small problem. I cannot actually bring that page. Nagita, can you do me a favor and remove me as a presenter? Maybe that actually solve the problem.
Just a moment.